Okay, so in that sense, thank you everyone for joining us here today for this webinar and also for your interest and participation in this competition. My name is Hrvoje and I'm one of the co-organizers of this competition, of this event. And as you can see, it is fully organized within the IEEE organization, to be more specific, within the Region 8 section and its Climate Challenge series. This competition is focused on AI in enhanced weather forecasting. So in that sense, you're all aware with all the incentives for this competition. We have all seen the recent climate changes, the extreme weather events that are happening. And also, on the other hand, has been a significant increase of weather data availability, both in real time and both being open source. All this provides a very, let's say, fertile foundation for implementation of AI, or to be more specific, ML or machine learning techniques within this area. Therefore, we have designed this competition in order to leverage these multi-source and multimodal weather data that are now available and combine them with statistic and machine learning algorithms. All together just to generate more accurate and more reliable short-term weather forecasts. Therefore, the main task of this competition is for you to generate 7 days ahead weather forecasts on hourly resolution for 2 variables in each of the 3 case studies that we have implemented. Our goal here is to basically gather all the experts in these domains, both the meteorological domain, both the AI and ML domain, and also exchange approaches and algorithms between all the participants, such that we are able to pinpoint guidelines towards weather coverage of improving the accuracy of weather forecasting with the approaches that we have mentioned. From the case studies that we have selected, there is a savanna preservation case study, the clean urban air, and the resilient fields case studies. So the first one is focused on the Masai Mara National Reserve in Kenya, which is basically an ecosystem of grasses, shrubs, bushes, and scattered trees. So it's a special type of environment for which we have selected 2 meteorological variables, namely the air temperature and the relative air humidity. For the clean urban air, we have selected the Manama city in Bahrain, which is basically an urban city area for which we want to predict or forecast the relative humidity and something which is called the US Air Quality Index. For the final resilient fields case study, we have chosen the Slavonia region in Croatia, which represents the Southeast Europe wheat fields, where we want to see how good we are at forecasting the solar radiation and the total precipitation. So from this, you can already see that we have been choosing 3 completely different microclimates, let's say it that way, with specifics and with different importances towards global weather and preservation of these unique areas. Therefore, also the meteorological variables that we have chosen coincide with the most important influences on the selected areas themselves. Regarding the competition itself, as you have been able to see in the competition guidelines, we expect you to form teams from 3 to 5 individuals, where 5 is, of course, the hard limit, but also if you have fewer members within your team, let's say 1 or 2, you are free to participate. However, keep in mind that you will be losing a bit of the competitive edge since you don't have support from a larger number of team members. We encourage you to utilize all other available open source data. However, it is your responsibility to ensure that this data is publicly available and under no commercial licenses. Additionally, we don't give you any guidance on the method for you to use for data fusion and the forecasting algorithm itself. So it can be statistical, it can be machine learning based, it can be a blend of many different approaches. Therefore, we just want to see your approaches, your ideas, your data which you would like to use, and eventually see how good you are at forecasting the selected weather variables. From our side, we want to compare the accuracy and the scalability of your approach, and therefore we will provide 50% of the points for the most accurate predicted variable, so the variable with the lowest RMSSE value, while the remaining 50% of the points will be provided by joint contribution of all the 6 weather variables. I will later explain this in more detail so that you'll have a clear overview of the scoring for this competition. The evaluation itself will be conducted on future variables, future values which are still not recorded. Therefore, we ensure a fair evaluation for all the participants of this competition. What we have already provided to you are the historical measurements, measurements that we have basically downloaded and fetched through OpenMeteo API. So you have at your disposal the historical weather measurements, historical runs of weather forecasts, and also future forecasts which are necessary, for example, for the evaluation of your algorithms and approaches. You can find all these data within the competition data file, which is available readily at the IEEE data port, where you have separate folders for different case studies, where each of the case studies has their own data set, as you can see here. Also, keep in mind that the current set of features, for example, if you will opt for a machine learning approach, the current set of features, the X-test and the X-train datasets, are exemplary only. So you are free to use them within your approaches, but you are also free to modify them and use them in any other way that you see fit, as long as you are able to explain it and as long as you are using open source data, which is readily available to everyone. In that sense, we have also provided you APIs, API examples for fetching different types of data from the OpenMeteo API, and you can find them all within the competition code and scripts files, which are also available at the data port. Additionally, we have provided you with a simple code with a Python script, which implements the RMSSE scoring function, which is used within this competition. To complete it all, we have also provided a simple benchmark example where we have downloaded from OpenMeteo the ECMWF forecasts for the 3 case studies and the evaluation period of this competition, and calculated the RMSSE scores for all the selected locations. Now, regarding the timeline of the competition, so as you have seen, the competitions have started with the beginning of October, for which we have provided you with an initial evaluation data set starting from 24th of September to 30th of September. You can find this here. It's already created on the IEEE data port. The competition itself will end on 1st of November at noon, at 12 p.m. UTC time, for which you are encouraged to submit your solutions, which actually encompass the time period from 13 p.m. on 1st of November to 12 p.m. On 7th of November. So that's an additional week on which we will conduct the final evaluation. So here you can see that just for your testing purposes, we have provided an initial evaluation data set, which encompasses 1 week of data, which has already been recorded, while for the final evaluation and the scoring, on top of which we will determine the winners, we expect you to submit the forecasts, which are starting from November 1st up to November 7th. So this here will be the final evaluation data set, which has not yet been recorded. It will be in the future, and after that, we will calculate the scores for each and every submission and announce the winners on November 11th here. As a follow-up of that, top 5 team or their representatives will attend the IEEE IHDC conference, which will be in Bari in Italy from 27th to 30th of November, where we expect you to prepare 4-page IEEE style manuscripts and the presentation for the conference. within which you will explain your approach, the data that you have used, the algorithms that you have chosen, and their evaluation, which will all finally be combined and published in IEEE Explore database. So for the evaluation of results, we have opted for using the root mean squared scale error, which has been proven several times as a fine scoring function for, let's say, time series data analysis, within which we will be comparing the actual weather data recorded, which is still unknown. It will be recorded in the future after the time after the submission time, and of course your AI calculated predictions. As I have mentioned earlier, as a final scoring, we will be choosing the smallest RMSSE value in your solution, so the most accurate variable that you have been able to forecast, and combine this part with the average score of all the variables together. So here we choose your most accurate forecast and the score for it, and combine it with the average of all the variables together, where the lowest sum of both of these scores will finally be implemented in the leaderboard, and on top of which we will decide who the winners actually are. So this is just to see how accurate your forecasts are. So this is the most accurate part, and also how scalable they are. So how well does your approach generalize to all the variables within these 3 case studies that we have mentioned earlier. Okay, so finally, how to submit your solution. So since this competition is hosted on IEEE data board, you will be required to create an IEEE account. So free account is also enough for you to participate in this competition. Basically on the challenge site, you click on this window to log in and enter submission, which leads you to another page with 4 separate windows. These 4 windows help you to submit your solution and give also a few data regarding your team, which we will also use for promotion and analyzing the results. So here on this first page where you have scripts and data, we are not interested in analysis scripts, but what we want to see are the results and files, which is the most important part to us, where you will actually submit your weather forecasts. The weather forecast that you generate should be provided in a zip file, where they will contain the 7 days ahead predictions, starting, of course, as mentioned, from November 1st, 13 UTC. So 1 hour after the deadline, up to 169 hours after the deadline. The zip file itself should contain 3 submissions, so 3 CSV files, 1 for each of the case studies, so 1 for the savanna preservation, 1 for the clean urban air, and 1 for the resilient fields case study. As you can see here, we have already provided you with the templates for these sample submissions. So please enumerate them by encoding them with their respective case study. Each sample submission should look like this, where, for example, for the savanna preservation, you have vector elements which go from 0 to 167. So this is basically 7 days ahead on hourly resolution. And they should also encompass the location ID, which tells us, okay, which case study does this file belong to. The starting dates and the ending dates should go according to the testing period, so from November 1st, 13th to November 8th, 12th UTC. The variables correspond to each of the case studies. So for savanna preservation, this is the temperature and relative humidity, while for clean urban air, it's the humidity and air quality index. For resilient field, it's precipitation and global tilted irradiance, as you can see here. So here's how it should look like for each of the 3 case studies, where you're just obliged to change the timestamps according from this evaluation time set to the testing time set. Okay. Once you have zipped all your forecasts and uploaded them in the scripts and data part, You should also provide us a few more information about your team in the metadata window, for example, your team name, the team members with some additional details if you're able to provide them, and some internal links, for example, such as personal website, LinkedIn, GitHub, or something else. So you'll use these data to basically promote all the participants and teams within this competition, and also as a follow-up of this competition. Also, there is the abstract window where we would like for you to give us some more additional information, like your expertise, the data sets that you have used, approaches, and so on, which will also be necessary for you to write the IEEE paper in case you will be one of the winners of this competition. And the final analysis window is not important to us, and you don't have to provide any files or information within these details. Once you do this, you're able to generate a preview of your submission, and of course, finally submit the analysis or submit your forecasts for us to evaluate them and finally find out who the winners of this competition are. So with this, I conclude the informational part about the competition itself. There will be, of course, a Q&A session at the end of this presentation where you can ask further questions in case you're interested. And me, myself, I would like to continue by showing you one example of AI-enhanced weather forecast that we have done within our LARES laboratory, which is part of the University of Zagreb in Croatia. So within our approach, we wanted to generate more accurate and more reliable weather forecasts. Also, by doing it, bridge the gap between forecasts and end users themselves. And finally, use this enriched data for decision support in many smart and precision sectors, such as agriculture, urban sector, or even energy sector. We wanted to do this by utilizing different data sources, such as localized meteorological stations, many different forecasting systems, so not just one single numerical weather forecast model, and even satellite and radar imagery. Just to remind you, you are also free to use all these different types of data as long as you ensure they're open source and available to everyone. Further on, our approach is based on utilizing all these data sources within our AI algorithms such that we can actually achieve localization of weather forecasts, correction of weather forecasts, even their transformation and tailoring towards end-use application of these weather data. Just to give you one example, I'm showing you here a map of Zagreb within which our laboratory is situated. And just a 4x4 kilometer square, which is a typical example of weather forecast resolution. So if you compare this square with the satellite image of land surface temperature, you can see how the actual air temperature varies significantly within this squared area, while the forecasts themselves provide you with a single number for this. So this was a clear indicator for us. There is still room for improvement, for localization, for capturing the microclimate of certain areas, and providing even more detailed and more accurate weather forecasts. So our methodology was based on utilization of in situ meteorological measurements and different weather forecasts. We were trying to model the actual forecast error and perform forecast corrections. So this is a typical time series machine learning problem where we use different features, for example, lag features, rolling windows, date times, and so on, such that we are able to utilize this data in our machine learning algorithms. We tried two different approaches. So one is the recursive approach with LGBM, so the dynamic propagation, I'll show this part later, and the one-shot or so-called MIMO approach with the TABNet, the neural network-based model. Of course, different machine learning options like Optuna hyperparameter optimization and time series cross-validation strategies, just to ensure that we are doing it the right way. So we were able to use our own meteorological station, which is at the top of our faculty, at the top of our laboratory, where we have 1-minute resolution measurements of different weather variables, such as air temperature, pressure, humidity, solar irradiance, wind speed, and so on. And from this, we created 2 separate scenarios where for one, we have used the numerical weather forecasts from Aladdin HR model, which is our national meteorological institution model, which they use for generating forecasts. And we have used LGBM for dynamic propagation and forecasting of air temperature and humidity, as well as the global solar irradiance. In the second scenario, we were using open weather forecast tabnet with one-shot approach for forecasting air temperature, humidity, and precipitation itself. So within the first approach, you can see here that we use the dynamic approach, the dynamic propagation approach, where we generate corrected forecasts from 1 hour ahead and then plug them into our model and extend this approach all the way to 24 hours ahead. For this, we use the LGBM model, of course, tuned on mean absolute error. We use inherent regularization of the model, early stopping of tuna for hyperparameters, and so on and so on. These are details of our machine learning approach. By doing this, we were actually able to significantly improve the Aladdin forecasts. For example, on a 1 hour forecasting horizon, the average air temperature error was reduced from 1.6 to 0.6 degrees Celsius. And you can see here that on the overall horizon of 24 hours ahead, the error, the blue line, the error of the Aladdin forecast was significantly reduced. So even 24-hour ahead forecasting horizon, we are able to reduce the error by 0.3 degrees. Same thing applies to other variables that we have utilized here. In motion, in real-time operation, basically this looks like this, where with the blue line you have the actual measurements on the weather station. With the green line you have Aladdin forecasts, which are generated every 4 hours, because large numerical weather models require heavy computation times and also demand, so it takes them around 3 to 4 hours to generate them. While we were providing corrections every hour with our machine learning models, since we were collecting localized weather measurements and running them every hour just to see how better can we do it when compared to these forecasts. Within our second scenario, within our second approach, we were considering the open weather service, which is actually another blend similar to OpenMeta, where they are using different data sources, from radars to weather stations to different meteorological organizations and their forecasts, and they're already using some types of AI or ML models to enhance these weather forecasts. So what we did, we downloaded a lot of their data and tried to use the tabnet model, which is basically a neural network model specifically tailored for tabular data. And since it's a neural network, for you that are more familiar with these models, we were able to do a one-shot approach where we run the model once and generate 24 outputs for 1 day ahead of forecasting. Again, some details about this approach from inherent regularization, early stopping, so on, but it's not so relevant for this. By doing this, again, when compared to the open weather service accuracy, we were able to achieve better forecasts. For example, the air temperature accuracy for 1 hour ahead has been reduced by 0.2 degrees Celsius, or for 24 hours ahead by 0.3. Here it's quite interesting to see that this blue line, the error of the open weather forecast, has already got this decline here, which shows us that they are already implementing some type of machine learning corrections of the weather forecast that they are receiving. But still, by utilizing the localized measurements, we are being able to further reduce this error or to further improve the accuracy of the forecast themselves. Same thing applies for humidity and total precipitation as other variables that we were considering in this case study. Key findings of this example is that we are actually able to design and implement a machine learning-based corrector of weather forecasts. So this is not an approach where we are generating a meteorological model based on AI. We are just designing a corrector of the forecast that we are achieving. And by doing this, we are able to achieve significant accuracy improvements from 10 to 60% for localized measurements. We compared the recursive approach, which is great for nowcasting, meaning that it's more accurate on really short horizons, and one-shot approach, which for us showed better results in overall improvement for, let's say, 1 day ahead forecasting. Also, we have noticed that the radiance and precipitation data are quite more demanding. They require perhaps additional data, maybe satellite or radar data, and they also require different validation strategies. But we have also included them in this competition for you to tackle these problems and hopefully show us even more better results as a part of your submissions and findings during participation in this competition itself. And with this, I would conclude the part of my presentation and start also a Q&A session for everyone present here in case they wish to give some questions regarding either the competition itself or our approach that we have presented. So thank you for attention, and please, if you have any questions, feel free to join and say. Thank you, John.
Hi. Well, this was a great presentation. Thank you very much. We have, well, I have one quick question for you, just for clarification. For the score, it's 50% is the one variable out of 6, right? Not one area out of 3. That counts for 50%.
Yes, one meteorological variable out of 6 of them.
Okay. All right. No, this is clear. Okay.
Excellent. Thank you.
Thanks.
Any other questions, please? Okay. I hope, if there are no other questions, of course, I hope that this presentation was useful to everyone. I hope that now you have a clear overview of the competition itself, of the demands and the actual guidelines and the scorings and everything. I hope it's all clear now. We will also post this presentation on IEEE Dataport so that you are free to reflect on everything, to have also all this data available for you to download. In case you have any further questions during the duration of the competition, feel free to ask them also on IEEE Dataport or through any other channel. Try to get to us, and we will try to answer them as quick as possible, such that you are able to further participate and submit your forecasts. And in that sense, we are looking forward to it, to receiving all your submissions, to checking all your approaches. I hope it's also as interesting to you as it is to us. And we would like to thank you for joining us in this webinar and also wish you good luck in submitting your results and forecasts. Okay.
All right. Thank you very much. Bye.
Thank you.